Hello everyone, today I'm going to show you a project called Coil Gun. Before going into details, let us see first a small demonstration of the project, what it does. Okay, you saw the demonstration. Now I'm going to explain how a single coil gun works. And here in this project, I used a very simple switching called SCR switching. And in the next video, I'll show you other types of electronic switching and also multiple coil gun to achieve higher muzzle speed. This is the photograph of the coil gun. The main part of a coil gun is a coil and a iron or any other magnetic material slug. When electric current passes through in the coil, magnetic field is created around the coil. If an iron slug is brought into the vicinity of this magnetic field, the field will try to align small magnetic domains in the coil iron, which results in an attractive force on the iron. The iron is pulled inside the coil. When the iron slug reaches the other end of the solenoid, the opposite magnetic field gradient will force the slug into the center. Thus it starts oscillating within the solenoid. When the slug reaches at the center and the switch is off, then it can go out of the solenoid with a speed, and some part of the electrical energy is converted into the mechanical kinetic energy. This slide shows an animation about what happens to an iron slug if it is brought near to an energized coil. The slug gains momentum and continues to move forward, and then it is pulled back. This slide shows the coil with a switch in the circuit. When the slug reaches at the center of the coil and the current is switched off, the slug will move with some gained speed. There are several types of electronic switch that can be used for a coil gun. The simplest is to use an SCR. A MOSFET or an IGBT or can also be used as a switch. Each of the switching mechanism has their advantages and disadvantages. SCR switching is the simplest of all. Turning a SCR on is simple. It needs only a small amount of gate current. Then the anode and cathode will start conducting. Once an SCR is on, it stays on until a certain minimum current called holding current is reached. So the on time depends on the coil inductance and the energizing capacitance. For a single coil gun, it works well. For the MOSFET and IGBT, both of them can switch with a precise timing. MOSFET switches are faster than the IGBTs. MOSFETs and IGBTs are used in multiple coil gun. In this project, I am going to use a simple SCR switching. This slide shows an SCR switch for the coil. An SCR is a 3-terminal device: anode, cathode and gate. It needs a very small current at the gate, like 5 to 50 milliampere, to trigger the device. Once it is triggered, it starts conducting until a minimum current is reached, called a holding current. The on time entirely depends on the capacitance, and the inductance of the coil. After designing the coil, a capacitor should be chosen such that the on time remains less than the time taken by the projectile to reach the midpoint. To make the coil for this coil gun project, I took a 12 centimeter long plastic pipe of external diameter 9.8 millimeter. Two rings were cut from a plastic sheet and glued onto the pipe to make a coil former of length 45 millimeter. I used AWG20 copper wire, 300 turns multi-layer, and the outer diameter becomes 26 millimeter. The inductance and the resistance of the coil was measured with an LCR meter. The inductance I found 635 microhenry and resistance 0.6 ohm. Now if current I flows through this coil, the magnetic field created inside the coil axis can be expressed by this equation. These are the photographs of the practical coil, the plastic pipe and the coil, and the length is about 45 millimeter. As a projectile, I cut some nails of 4.2 millimeter diameter. Cut lengths varied from 20 millimeter to 35 millimeter. Little shorter than the coil length, which is 45 millimeter. Mass of the cut nails were measured using a kitchen balance, approximately 5 to 7 gram. The force experienced by the projectile is expressed by this equation. If a current I of 20 ampere is flowing through the coil, the amount of magnetic field and the force exerted on a 20 millimeter long projectile is shown in the second plot, and the first plot shows the magnetic field inside the coil. The magnetic field reaches at its peak at the center of the coil. The interesting plot is the second one. The force on the projectile, you can see the force is attractive and maximum at around 17 millimeter. Then goes down to 0, about 30 millimeter. Beyond that point, the force is negative. That means the projectile will be pulled back inside, which is called suck-back effect. Now for the same coil, if we take projectiles of various length, 20, 30 and 40 centimeters, what will be the effective force on the projectile? As you can see, the 40 millimeter long projectile, the force is positive up to 42 millimeter. Beyond that point, it is negative. For smaller projectiles, this distance is a little shorter. To have an idea of how the force on a projectile varies with distance inside a coil, I used a iron nail and a spring balance and a coil. About 3 ampere current was allowed to pass through the coil. The iron nail attached to the balance was put inside the coil. Varying the distance, we can measure the force. This is shown in the main video. Suppose a coil is carrying a current I. Projectile sucked in the coil, and at the right moment the coil current is switched off. Under this condition, the velocity of the projectile can be expressed by this equation. We can see that for a fixed coil and projectile, the exit velocity depends on the current I. Higher the current, the higher the speed. It is possible to reach the speed of an ordinary air rifle pellet. The speed is around 300 meters per second. Using high current, it is possible to reach that speed. The equation for a speed for a 5-gram projectile using the designed coil is plotted against the coil current. It is a linear relationship. Higher the current, higher the speed. There is an easier way of roughly estimating the speed of a projectile. As we discussed in the coil gun, a capacitor is first charged and then discharged into the coil. Roughly 1 to 2% of the stored electrical energy is seen to be converted into a kinetic energy of the projectile. Using this equation and considering 2% conversion efficiency, we can find the speed of the projectile. As you can see, there is no mention of the coil current here. As current is proportional to the circuit voltage, higher the current means higher the voltage. The plot for a projectile speed against the capacitor voltage is shown here. The same equation is plotted here against the capacitance. As you can see, the increase is slower. As we have seen before, higher capacitance also makes the on time slow longer. So increasing the higher voltage is to achieve higher speed is essential. Considering the average positive force active up to 40 millimeter, 0 to 40 millimeter distance, the projectile will subject to acceleration and then exit at a constant speed. So the transit time can be expressed by this equation. This is plotted here. As you can see, higher the speed, the transit time gets shorter and shorter. So we have to adjust the on time with the speed as well. So to achieve higher projectile speed, the voltage should go higher and the capacitance should go lower to shorten the on time. This slide shows the complete circuit diagram of an SCR switched coil gun. To achieve higher projectile speed, we need a DC voltage higher than 50 volt. I used a small transformer to convert mains 115 volt to DC to AC 80 volt. Then a bridge rectifier is used to convert this AC into DC, and it is filtered by a filter capacitor of 200 microfarad. At this output, we can get approximately 110 volt. A switch is needed here, and then a 500 ohm resistor in series to charge the capacitor. This resistor, that is 500 ohm resistor, is not essential, but it is only here for protection. Once the SCR is switched on, it is triggered, then current will, it can show, if the resistor is not there, it can make a short circuit. Higher current can pass through and there will be a suck back effect. So to reduce that accident, this 500 ohm resistor is a kind of essential here. We can have an idea of current and on time using simulation. I use LT-SPICE for simulation, and it is free for anyone to use. Simulation shows that for a 100 volt capacitor voltage and the capacitance of 3500 microfarad, the peak current can go as high as 75 ampere and on time is around 6 millisecond. Now if the voltage remains 100 volt and the capacitance is now 1500 microfarad, then the peak current will go little lower. Now it is 65 amp, but the on time is nearly half, only 3 millisecond now. If we keep the 1500 microfarad capacitor and use various voltage like 80 volt, 120 volt, 150 volt and 200 volt, we can see the peak current goes higher and higher and higher. But the on time almost remains the same at 3 millisecond. So higher the voltage means higher the current and higher the speed as well. For simple SCR based coil gun circuit, we have to consider both. If we increase the voltage, the speed of the projectile will go higher. However, its transit time will also get shorter. For short length coil, we can see some effect of suck back effect. Then we have to reduce the capacitance. Two circuit boards are built with the similar kind of SCR. This is SCR, the energy storage capacitor, and the resistor. And in one board I used 1500 microfarad, and in another board I used 3500 microfarad capacitor. This is the photograph of the complete coil gun. Of course, two power supplies are needed. Those are not shown here. As shown previously, one high voltage power supply is needed for the coil circuit, and the another one low voltage supply is needed only to trigger the SCR. I built two high voltage supply. One is 110 volt, another one 160 volt, using transformer and rectifiers. The other 5 volt source I just used as wall mount supply. Once the coil is triggered, the projectile gains speed and hits a target. Next comes the task of determining the speed. Using a sound recording app in a mobile phone and analyzing the audio graph using another app, it is possible to roughly estimate the speed of the projectile. In my case, I determined the speed 25 meter per second to 35 meter per second. You'll find that this method explained in many places in the net. In the next video, I'm going to use a MOSFET as a switch and try to show its advantages. You'll find that some people are making multiple coil gun. I also have a plan to show you such a kind. However, one thing should be noticed, that if we use similar kind of coils and capacitors, double the coil does not give you double the speed. In fact, it is less. It will follow a pattern like that. So to increase the speed twice, we need 4 coils. These are the references I mainly use to design the coil gun. To have an idea of a force exerted on the iron nail by an energized coil, I used a power supply, a coil, a iron nail, and a spring balance. The current is adjusted to around 3 amp to create sufficient magnetic field. Now the nail, which is cut from a longer nail, there is a marking on that which determines the length of the coil. And a spring balance is used to measure the force exerted on the nail. Now you can see that as the nail go deeper and deeper into the coil, then the force goes up, and then again it goes down. So there is an optimum force, maximum force somewhere in between. And from the marking on the nail, we can have an idea where is the location of the maximum force. So exactly at that point, our coil should be switched off. This is the coil I made, plastic pipe, and the coil former was made with 2 other. This is the nail, and a piece is cut from that. And this is the circuit that I built using a capacitor SCR. And this is the final coil gun, and I am placing the projectile and the capacitor is charged using a switch. Now the switch is off and the gate is triggered, and you can see that the nail piece is fired. You can see the projectile going out at a high speed. It is being loaded with the projectile. Gate is triggered and it is fired.